Yeah. Good evening, uh, good afternoon, or good morning, everyone. And thank you, George, for the introduction and also the opportunity, giving the opportunity to present our work at GERAD seminar. So this title of today's talk is Guaranteed Cost Equilibrium in Infinite Horizon Linear Quadratic Differential Games. And this is joint work with my graduate student, Aniruddha Roy. So the outline of the talk is, it has two parts. The first part is on linear quadratic differential games with output feedback information structure. And we study an equilibrium concept called as an output feedback guaranteed cost equilibrium. And the second part is on linear quadratic differential games with uncertainties, modal uncertainties. And a related equilibrium concept is what we call a soft constrained output feedback guaranteed cost equilibrium. So the first part, some portion of the work is published, not the entire part, but in the first part. The second part is the work in progress. So here, basically, the main problem that we are interested in studying is infinite horizon linear quadratic differential game. So here we have the dynamics, that is, the system evolution is influenced by n players according to the following linear time invariant dynamics, and the players have access to each player has access to an output. Yeah, and each player is interested or is seeking to minimize the following quadratic objective. So here we assume that the matrix is Qi is positive semi-definite and the matrix Ri is positive definite, and we have some technical assumptions. So here this symbol scripted greater than is positive semi-definite, and scripted strictly greater than equal to 0 is positive definite. So the information structure that we assume is the output feedback information structure, that is static output feedback information structure. So what is the motivation for studying these games is basically in the control of networked multi-agent systems, agents will have only local information in the local state information, but not the global state information. So when you have large number of players, players will, it may be too costly to get information from all the states of all the agents. But so here, and also when the information is available through sensors, so the states are hidden variables, but we only get observations. So in that sense, each agent has only some local information. And it is captured by the idea that the matrix Ci has a rank which is strictly less than n. That's idea. And the equilibrium concept in these games, the equilibrium concept we are interested in studying is naturally, we look at, because the information structure is static output feedback. So a related equilibrium concept would be an output feedback Nash equilibrium. And yes, yes,
so
Josh.
what is the meaning of this word output in the definition of the equilibrium?
So here,
It's
that is
not very
players,
usual.
the players are restricted to using these strategies. UI
Okay.
is a static uh, output feedback. Players are restricted to use these instead of static state feedback. They can only use these strategies. That's the information structure.
Okay, I see. Okay, thank you.
Is it clear, George?
Yes, thank you.
So then we call a particular strategy as output feedback Nash equilibrium strategy if the following inequalities hold true. And the sufficient conditions for existence of a static, the output feedback equilibrium can be obtained from this work by Engvarda. And they are related to solvability of these coupled algebraic Riccati equations. And if the stabilizing solution of the algebraic Riccati equation, in the sense, a stabilizing solution of the algebraic Riccati equation is characterized by characterized as that this matrix is stable. That is, the eigenvalues of this matrix must be strictly less than 0. And once we find a stabilizing solution of the coupled algebraic Riccati equation, then the Nash equilibrium strategies can be obtained by solving this equation. So once we get a solution Pi, which is stabilizing solution, then one can actually solve for the Nash strategies by solving this equation. So what are the difficulties? So now we look at difficulties associated with solving the coupled algebraic Riccati equation and also solving this equation to obtain the Nash solution. So a coupled algebraic Riccati equation usually involves solving uh, uh, n into n plus 1 divided by 2 multivariate polynomial equations of degree 2 in this many number of variables. And of course, there exist some iterative methods, but they are very sensitive to initial conditions and the convergence is usually not guaranteed. Then the next issue is we said that these feedback strategies can be obtained by solving this equation, and for solvability of this equation is related to that the solutions of the algebraic Riccati equations must satisfy the following structural constraints. So basically, to summarize, to synthesize a output feedback Nash equilibrium, we have to solve the coupled algebraic Riccati equation, and a stabilizing solution of the coupled algebraic Riccati equation must also satisfy the following structural constraints. So we have stability requirement and certain structural constraints, n structural constraints on the solution of the coupled algebraic Riccati. So these are sufficient conditions. So we'll see, we see an example now to see if these sufficient conditions are feasible or not. So we consider a 3-agent network, and the dynamics of each agent is given as follows. And here, agent 1 has only local information, that is information of his own state and also state of player 2. Player 2 has state information from 1 and 3, and 3 has information of only player 2, agent 2. And these are the objectives. And the coupled algebraic Riccati equation results in 18 multivariate polynomials of degree 2 in 18 variables. And we see that the KR does not have a stabilizing solution satisfying these structural constraints. So that means the sufficient conditions are inadequate to say if an output feedback Nash equilibrium exists in this game. So in a sense, this is the main motivation for our work. From the following first two limitations, now we ask the following question: is there a broader class of strategies that satisfy output feedback strategies that satisfy an equilibrium property? Here, term broader refers to the idea that if Nash strategies exist, they must contain in this larger class of strategies. That's a problem statement here. So in the main motivation, to really address this problem, we look in the literature of network multi-agent networks, or at least the optimal control with structural constraints, and at least the issue in optimal control, the problem has been addressed with the following idea of suboptimal control. That is, in a typical optimization problem or optimal control problem, we look for a control that minimizes this cost function. But in a suboptimal control, we can actually trade off. That is, if we have some additional restrictions or additional constraints on F, and it is possible that this optimal solution may not satisfy those structural constraints, then what we can do is we can actually trade off for optimality by looking for a suboptimal solution. That is, we can look for controls which guarantee that the cost is less than some threshold delta. Yeah. And then search in this set if we have a control actually that satisfies the structural constraints. Yeah. So that's the idea of suboptimality here. And notice that once we have an optimal solution, that is also a part of a suboptimal solution. Yeah. That means if I choose delta greater than this particular value, then we see that this F star is already included in the suboptimal solution. Now, with respect to optimal control problem, these actually translate as, in the sense, if we just study the single player problem with a static state feedback, we see that the optimal solution is obtained by, we can obtain the optimal solution by solving an algebraic Riccati equation. But the suboptimal solution, when we see the suboptimal solution, that is given a delta, so we look for all the feedback controls that guarantee that the closed loop system is stable, but guarantee a cost less than delta. Yeah. And a sufficient condition for existence of such an F is we require the following inequalities to hold true. That means I look existence of a positive definite P such that the following inequalities hold true. That is, once I obtain a P, then I can synthesize an F as follows. But these inequalities can be equivalently written as following linear matrix inequalities. And notice that here we are not solving a problem like a polynomial problem, but here we are only solving a set feasibility problem, right? In the sense, we are just searching for a P that satisfies these inequalities. Yeah. So in some sense, this problem is much simpler to solve than an optimal control. And there exists an efficient, there exists efficient methods for solving LMIs. So now the idea is, can we extend this idea to a multiplayer setting? So these are known results for single player case, that is an optimal control or suboptimal control problem. The idea is, can we extend this idea to a multiplayer setting? So once, if we want to extend this idea to a multiplayer setting, we have to have an equivalent notion of a best response of the player. So here we have an equivalent idea called as a guaranteed cost response. So, so a guaranteed cost response is basically defined as, like, given a cost profile of players, a guaranteed cost response of player I for a given strategies of other players is defined as set of all feedback strategies that guarantee that the player I's cost is less than his cost. That is his his cost profile delta. Yeah. That is basically the set of all strategies that ensure that player I cost achieves the desired upper bound. But here the question is how this guaranteed cost response is different from a best response. So say for instance, if other players use the strategy F minus I, and if other players deviate from F minus I to F tilde I, the best response also changes. Similarly, the change in the guaranteed cost response is depicted as follows. Here we can see that the guaranteed cost response is a little weaker, in the sense players can still use their strategy that they have been using, even if other players change their strategies, as long as player I's cost meets the desired upper bound. In some sense, in guaranteed cost response, the player I's deviations are a little weaker compared to the best response. So we can now, once we have the guaranteed cost response, we can now come up with the notion of an equilibrium, which we call as a guaranteed cost equilibrium. So given cost profile of the players, a strategy profile is called as a guaranteed cost equilibrium if for every player I, the following condition holds. That means this is similar to the Nash, that is Nash equilibrium, but here this is with respect to the guaranteed cost response. So in Nash equilibrium, we give this fixed point notion with the best response. So here we give this notion with respect to the guaranteed cost response. And so the main idea here is once the players are in guaranteed cost equilibrium, no player has an incentive in deviating from the current strategy, as each player has achieved desired upper bound on her cost. And one way to interpret this equilibrium is, suppose if a social planner, after knowing the cost profiles of the players, if proposes a particular strategy profile to the players, then each player's cost achieves the desired upper bound by obeying the proposal given by the principal when other players do the same. So any questions here so far? on the equilibrium concept.
How it can be justified from a behavioral point of view? Why a player would necessarily settle for this kind of equilibrium? Of course, when you look at individual deviation, starting from the idea that players would want to have a guaranteed minimum cost, everything is consistent. But can you say something additional in terms of why one player would not want to deviate outside of this scheme? Because this reminds me a little bit incentive strategies. You want to stick to incentive strategy, but it may be in your best interest to go to Nash instead of. So I'm a little bit confused here in terms of the behavioral support of the equilibrium concept. I understand the definition and how it works, but what can be said about if all players are happy with this, why a player would not go for completely something different? Is it any thought about it?
So here I see it has, you can correct me, George, with the following interpretation I have. So here I feel it has some relation to the idea of correlated equilibrium. So in a correlated equilibrium, there is a principle. Here the principle is proposing a certain strategy profile to the players. And it is equilibrium in the sense that when when other players obey the proposal given by the principle, then it is optimal for a player to obey. So
I
that's
got
the
it.
interpretation.
I
Yeah.
got it. Excellent explanation. Thank you,
Yeah.
Vishwa.
So yeah, that's the interpretation we have here.
Thank
So
you.
in fact, we see that in correlated equilibria can achieve performance very close to the Pareto one. In the sense, of course, they may not exactly equal to the Pareto one,
Of
but
course.
yeah. So here also we observe a similar behavior in our
No,
simulations and so on.
very nice interpretation. Okay.
Yeah.
Please
Thank you,
go
George.
ahead. Thank you.
So, here this guaranteed cost equilibrium is something not we have proposed. In fact, it is motivated by a solution concept called a satisfaction equilibrium that is studied in static games. But it's just inspired. They call this as a satisfaction equilibrium, and we call this as a guaranteed cost equilibrium because here we are working with costs, and in satisfaction equilibrium, one works with payoffs. Yeah. So now to really position this work, so the suboptimal control problem, that is single player problem, is a very well studied problem in robust control literature. In the area of multi-agent network systems, because the information available to players is a very local information, so naturally there will be structural constraints that come into play naturally. So the use of suboptimal approaches is kind of very prevalent in multi-agent network systems, and some of the references I have provided here, but there are many works. And as I said, that is with respect to the suboptimality part. And with respect to the static non-zero sum games, the satisfaction equilibrium, the guaranteed cost equilibrium that we are talking about is kind of inspired from the satisfaction equilibrium. And the use of satisfaction equilibrium in multi-agent in control literature, to best of our knowledge, this is the paper where we first notice that the application of satisfaction equilibrium in the synchronization problem in multi-agent network systems. And but this is a particular synchronization problem with identical agents. So a differential game framework, the guaranteed cost equilibrium in non-zero sum differential games, but applied to network systems were done by by us, that is Aniruddha and myself. So what I'm going to talk about now, some parts of what I'm going to talk about now are published actually in this IEEE control system literature. So once we have this guaranteed cost equilibrium, so we can also now study the properties of the guaranteed cost equilibrium. So the first property we show that is these equilibria have monotonicity property. So here the monotonicity is basically, so given a cost profile, and also I have another cost profile. So here the cost profiles are related by the idea that the expectation of player I in this profile is lower than that is the upper bound delta I bar. I mean, this has to hold true for all players. And if this is a guaranteed cost equilibrium set with this profile, and F bar circle is a guaranteed cost equilibrium, I mean, set with this cost profile, then we can show that these equilibria are contained in this equilibrium. Yeah. So there is certain monotonicity property. And suppose if we have a Nash equilibrium, I mean, if there exists a Nash equilibrium for the game, then we can also show that this Nash equilibrium is also a guaranteed cost equilibrium by considering this particular cost profile, because this is the design parameter, this is in our hand. Yeah. So, but this is can be only realized ex post. Yeah, we don't know this before. Once we know this is the equilibrium, then we can show that for this particular delta I cost profile, we can show that there is a guaranteed cost. And we can also obtain certain price of stability bounds for the guaranteed cost equilibria. That is, here the price of stability is the total sum in guaranteed cost at guaranteed cost equilibrium divided by the total sum of costs in cooperation. Uh, uh, so we can, since each cost in equilibrium is strictly less than delta I, so we get this natural upper bound. And the lower bound is directly follows from the idea that when players actually cooperate, their cost will be much lower, because I am here optimizing on a great and larger set. But here I want to ensure that I want to emphasize that this optimal cost in cooperation is solved as an optimal control problem, but not as a suboptimal control problem. Even in the presence of structural constraints, we can obtain this cost because we are solving an optimal control problem, but we may not be able to realize that cooperative cost. Because once we have structural constraints, we require that the solution of the associated algebraic Riccati equation has to satisfy some structural constraints. But it may not be possible for the controllers to satisfy that structural constraint. But this cost can be obtained. The advantage of, I mean, in a sense, so from this inequality, we can actually get what values of delta that cost profile should satisfy. In the sense, this immediately says that the summation of the cost profiles must be greater than their cooperative cost, the total cooperative cost. Yeah. Once we have these three properties, now we can ask the following question. So we have two questions. One is about suppose if I'm given a cost profile and also a strategy profile is given to me, then the question is when can I say that this strategy profile is a guaranteed cost equilibrium? Then the next question is, when can we synthesize, given a cost profile, when can we synthesize a guaranteed cost? I mean, how can we find a guaranteed cost equilibrium? So to answer the first question, so given a cost profile and a strategy profile, if we have the following sufficient conditions, that is, if there exists a positive definite matrix PI, that is, we need actually n positive definite matrices, such that the following inequalities hold true, then we say that this strategy profile is a stabilizing output feedback guaranteed cost equilibrium. So basically, the verification involves checking the feasibility of 2n linear matrix inequalities. But this is just a verification result, and it cannot be used for synthesis of guaranteed cost equilibrium. So the synthesis of guaranteed cost equilibrium requires that the guaranteed cost response is non-empty for a given strategy profile of other players for every player. So we have the next result, which actually provides sufficient conditions under which the guaranteed cost profile is non-empty, given the strategy profile of other players. So basically here, this result reads as basically, so given the cost profile of the desired cost of player I, and the strategy profile of other players, we require that there exists two matrices, Pi to be positive definite and a matrix Fi, such that the following matrix inequalities hold true. Then we can say that the guaranteed cost response of player I is non-empty. But notice that this inequality is not a linear matrix inequality, it's a bilinear matrix inequality. And the feasibility of a bilinear matrix inequality cannot be solved as a convex feasibility problem. And it has been shown already that the bilinear matrix inequalities are highly non-convex problems. And as a result, they cannot be solved as convex feasibility problems. Yes, that means we will not be able to test the non-emptiness of the guaranteed cost response using LMI solvers. But if the bilinear matrix inequality has a special structure, that means has a specific structure, we can test the feasibility of this bilinear matrix inequality using something called as a projection lemma. That is, we are interested in testing the feasibility of this bilinear matrix inequality, which has this special structure. Then we can show that the projection lemma says that the feasibility of this LMI is equivalent to the feasibility of these following two LMIs. But notice in these two LMIs are F independent. So that means we have so using this equivalence relation now we can actually test the feasibility of this bilinear matrix inequality by checking for the feasibility of two LMIs that involve only the variables Pi. Yeah, in the sense these are F independent. But projection lemma says something more also, in the sense once we have feasibility of these two LMIs, it actually says that there exists an F. Yeah. So that means I can find, in the sense, I get this F for free actually. Once I get a feasible P that satisfies these two LMIs, then I can substitute that P here. It is not a variable anymore. Then I can solve this LMI to get F. And actually, the projection lemma says that there exists an F. Yeah, because these LMIs, the feasibility of LMI is equivalent to feasibility of these two LMIs. So now we have the synthesis result. That is, using the projection lemma, we define the following matrices. Apologies for too complex notation, but I don't know any other way of representing them. Yeah. So we have the following synthesis result. So given the cost of desired cost of player I and the strategy profile of other players, so we define the following sets, and we define the set Pi as set of all positive definite matrices such that Pi belongs to the set X and its inverse belongs to intersection of two sets Y and Z, where the set X, Y, and Z are defined as follows. So here the set X is set of all positive definite matrices that satisfy this LMI. Y is defined as the set of all positive definite matrices that satisfy these elements. So basically, the idea here is the set X, Y, Z, these are all convex sets. Yeah, so that means we want to find all positive definite matrices such that the Pi belongs to this convex set, but its inverse belongs to intersection of these two sets. So once if this set is non-empty, then we can actually show that the guaranteed cost response is non-empty. And once the set is non-empty, then I can pick an element from this set. Then I can obtain the feedback control for player I by solving the following element. And this result directly follows from using the projection line. So basically, what this result says is the non-emptiness of guaranteed cost response of player I is tied to non-emptiness of the set Pi. But this set Pi, to check the feasibility of non-emptiness of this Pi, it cannot be tested again as a convex feasibility problem because of the following bilinearity constraint. Because now we can write this set Pi equivalently as requiring that the two variables Pi and Wi to be positive definite. We said that X is a convex set and Y intersection of YZ is a convex set. But these two variables are tied as the requirement that because the Pi originally is defined as Pi inverse belongs to this set. So now we can write this equivalently as this second variable Wi should be inverse of Pi. So this is due to this bilinear constraint, this set is not convex. But we can actually relax this, we can take a convex relaxation of this set by using the Schur complement, and we get a set Pi bar, but this set Pi bar actually is a convex set. Yeah. So now, so we solve an optimization, the following trace minimization problem, in the sense, we minimize the trace, but over the set Pi bar. And if the optimal solution of this optimization problem satisfies that the optimal value is equal to n, then we get an element in the set Pi. Okay? So basically now we are searching to, we are trying to find an element in Pi that is obtained by looking for a convex relaxation of Pi, and we solve a trace minimization problem over the relaxed set Pi bar, which is a convex set. Yeah. And this is a convex optimization problem. And if the optimal solution of this convex optimization problem is n, then we get an element in the set Pi. In fact, we can show that this set Pi is the boundary of the Pi bar. That is actually what happens. This Pi is a boundary of this set. So that is how we test the feasibility of set Pi. So basically, we can now come up with a best response type dynamics type algorithm to find the guaranteed cost equilibrium. That is, solve the optimization problem, and if we get the optimal solution satisfies this trace condition, then guaranteed cost response of player is non-empty. Yeah. So then we can actually synthesize the strategy Fi from, because since I know an element in Pi, we solving this LMI, I can now synthesize Fi. So we do this iteratively in the sense, at kth iteration, if I know the strategy profiles of players, other players is, then I can, we can synthesize player I's response, the guaranteed cost response, and we keep updating, keep iterating. We do this for each player and we iterate this process. And if it converges, then we get a guaranteed cost equilibrium. This is similar to best response dynamics. But here, notice that when we solve the Nash equilibrium, that also involves solving coupled algebraic Riccati equations. So the coupled algebraic Riccati equations, there are iterative methods that solve the coupled algebraic Riccati equations, but they also have a best response dynamics feature, because at every iterate we are solving an optimal control problem associated with the play. But the difference between this approach and that approach is, when we solve a coupled algebraic Riccati equation, we don't know if it actually converges to a stabilizing solution. So that stability check will be done after solving, after the iterative process converges. But here the stability requirement is embedded. That's the main difference with this approach. At the moment, we don't have theoretical guarantees on the convergence. So we have the following algorithm. This is the guaranteed cost response algorithm. And we have a couple of examples that illustrate our results. So we now we consider a three-agent network multi-agent system, but this is where we have full state feedback information. So the idea here is we want to compare the performance for this problem. There is an Nash equilibrium here. Here we are working with full state feedback. This is not the output feedback, or the output is exactly equal to the full state. Yeah. So we consider the following network where every agent has the complete state information of other agents. So these are the dynamics and these are the objectives. And for this problem, we consider all deltas to be same. And we observe that for delta I less than 1.7, we could not find guaranteed cost equilibria. And there exists guaranteed cost equilibria only when delta is greater than 1.7. And so these are the X in this graph. This is the price of stability. We are plotting price of stability against delta. And uh, the total cost in cooperation is obtained as this value. And for this game, there exists a unique Nash equilibrium, and this is the total cost of the players at Nash equilibrium. So we can actually now compute the price of stability associated with the Nash equilibrium that is shown in this red line. So here we have the price of stability now associated with the guaranteed cost equilibrium, but here note that each guaranteed cost equilibrium, so depending upon a value of delta I, we get the total cost of the players at guaranteed cost equilibrium, right? So this is the ratio of the total cost of the players at the guaranteed cost equilibrium divided by the total cooperative cost. And the minimum POS that we see in this example is at 1.03 or 1.04, close to 1.04. This is the point, and we have a lot of guaranteed cost equilibria which achieve a POS lower than the Nash equilibrium. So this is the point I want to refer back to the question asked by George. In a sense, here the guaranteed cost equilibrium has a feature of this correlated equilibrium. In the sense, we have a lot, the guaranteed cost equilibrium can achieve a performance very close to the cooperative one in some sense here. And that is illustrated clearly in this example. Yeah. So the POS equal to 1 is basically the which can be achieved by a totally decentralized control. But here, of course, we don't have a completely guaranteed cost equilibrium, do not achieve a complete decentralization, but it's very close to the cooperative. And for this game, a Nash equilibrium exists. There is a unique Nash equilibrium, and we have a lot of guaranteed cost equilibria that achieve a POS that is lower than the POS associated with Nash. So this is with full state feedback. So now we take the same example, but with the idea that we don't have, that is player 1 does not have state information of player 3, and also player 3 does not have state information of player 1. Yeah. So these are basically the dynamics and these are the objectives. So player 1 has only the state information of, his own state, and player 2. Player 3 has information of his own state and player 2. So again, here for this game, the structural conditions are violated, in the sense that means we cannot really comment if a Nash equilibrium exists for this game, because the structural constraints are not satisfied for this game. And for guaranteed cost equilibria, we observe that we get the guaranteed cost equilibria do not exist for delta less than 2.2, but for all delta greater than 2.2, we have guaranteed cost equilibrium exists for all delta greater than 2. And we can also, the minimum POS at guaranteed cost equilibrium, we observe that it is around 1.08. Again, it is close to the cooperative one. So we also tried some examples where the state variables, the number of state variables for each agent is a totally heterogeneous example. this is an output consensus problem. So basically, the idea is the agents have information of the outputs of their in neighbors, and each agent is trying to minimize. Each agent is trying to synchronize or with the local reference. So we can get the local reference signal as uh, average of the in neighbor outputs. The objective is to ensure that player I's output is close to the reference. Yeah, and it can be posed as a game problem. And we, for these parameters, we obtain the guaranteed cost equilibria, and these are basically the output consensus results. The errors are actually going to zero, and we get the price of stability here as around 1 point. Basically, the idea here is we can, in a sense, the guaranteed cost equilibrium can be used to study not only a homogeneous problem, but also the matrix cases as well. Yeah, so it's a general concept in some sense. So this is the first part of the seminar. Any questions so far before I move to the current work?
You can proceed, Vishwan.
Yeah, thank you. Thank you, Shaz. So next, the next problem, where at least the current work that we are interested in is basically about the linear quadratic differential games, where in the presence of modal uncertainties. So here, the modal uncertainties are basically the players don't have the exact knowledge of the system, but there are certain disturbances that are affecting their interaction environment. But agents have an idea that these disturbances are happening around some nominal system, and the nominal system evolves is a linear time invariant system. And we assume that these disturbances are basically deterministic disturbances with a finite energy constraint. Yeah. So here, players are interested in the following soft constrained quadratic criterion. So here, since there is a disturbance around the nominal dynamics, each play agent can have some idea about the disturbance. So, and that is actually captured by this performance criterion. So, and here again, we assume that the players use static output feedback strategies, and we assume that each player is minimizing the worst case cost. So that means each player is each player is minimizing this objective function, but not this objective function. So this is the worst case cost of the player. So in some sense, this DI, this DI is reflects the risk appetite of the player, because in this problem, that is in the worst case cost, if we solve this problem, the worst case disturbance is given as the inverse of the matrix D. Yeah, that means if the norm of DI is more, that means the player I is expecting that the worst case disturbance has a very small value, right? So that means the larger values of DI express that the player I is expecting that the worst case disturbance will have a small amplitude. In some sense, the player I is kind of underestimating the disturbance. So the norm of DI reflects the risk appetite of the player. So if player I is using a DI which has a larger norm, means that the player I is more risky in some sense. That's actually the idea here with respect to this performance criteria. So again, a quick review of the literature here. In the one-player case, this is a well-studied problem in the robust optimal control literature, and the standard reference is by Bazaar and Bernard. In a multiplayer setting, the works of Van den Broek and Engwerda, the study these games in the multiplayer setting. And there exists a geometric characterization of equilibria, and the recent paper gives a summary of these results. And the matrix case.
Vishwa, 10 minutes, please, if you want to leave a few minutes for questions.
Sure, Charles. Yeah.
Thank you.
Yeah. So, and in the matrix case, basically, we have, I mean, this review paper talks about the iterative methods related to the equilibrium concept in this reference. So basically, again, here we can also talk about soft constrained output feedback Nash equilibrium for these class of games in the presence of disturbances, and sufficient conditions for these existence of these equilibria are again related to solvability of these coupled algebraic Riccati equations. But here, one additional complexity is that we require, instead of one stability condition, we require that stabilizing solutions, I mean, the solutions of the care needs n+1 stability condition along with the following n structural constraints. So these n stability conditions are extra here, yeah, once we have disturbances. And again, we see that these conditions are too stringent, that they are very difficult to meet even for simple problems. So we can now again define, similarly following the previous work, we can define the notion of soft constrained output feedback guaranteed cost equilibrium. And given we have a similar verification result like the previous case, but here, because of these additional stability constraints, we have a additional bilinear matrix inequality in the verification result. That is a third inequality. But we can kind of bound this inequality with a manageable inequality and still write a little stringent, we can write this BMI, we can bound that BMI with an LMI here. And we can do the verification with the LMI solvers. But this is just a verification result. It is not a way to synthesize a guaranteed cost equilibrium. So now we have the following synthesis result. The sufficient conditions are related to solvability of these three matrix inequalities. And the first and the last inequality are bilinear. And we can, like before, we can also now use a projection lemma to actually talk about the non-emptiness of the guaranteed cost response. The difference with the previous result and this result is that we end up with a testing the nested feasibility condition. That is, first we look for the feasibility of the first BMI and the LMI. And then we obtain a set PI like before, the non-emptiness of this set PI. But so once the set is non-empty, we can now write these BMIs by fixing this PI and define the following LMIs. Yeah, so these LMIs. So that means basically we are looking for non-emptiness of another set which is dependent on PI. Yeah, so that is first I solve those two LMIs, that is BMIs, as if this set PI is non-empty, then I can define a subset of this PI which is defined as non-emptiness of another set. So if we show that this subset of PI is non-empty, then we can say that the guaranteed cost response is non-empty. So once we have disturbances, the non-emptiness of the guaranteed cost response will involve a nested feasibility condition. So that is the novel part here. So once we have this, this subset of PI is non-empty, then the guaranteed cost is non-empty, then we can actually obtain the controller by solving these two elements. But again, like before, we have, since it involves a nested feasibility condition, so here we'll have to solve two optimization problems over the relaxed convex sets. So here the set we defined is non-convex because of the bilinear constraint. So we obtain a convex approximation of this PI and solve the first optimization problem. So once we tested the feasibility of non-emptiness of this set, so we define the nested. I mean this set depends on the feasibility of the problem above. Again, we take this set is non-convex due to this bilinear constraint. So we relax, we get a convex approximation of this and solve another convex optimization problem, is a trace minimization problem. And if this trace, the optimal solution is n, then we get the subset of PI to be non. So again, we have an algorithm here. We solve the first optimization problem. Then we solve the nested optimization problem too. And then if again, I mean, we get the trace condition to be n, then this set is non-empty. That means the guaranteed cost response is non-empty, and we can synthesize player-ice feedback control. And we do this best response dynamics. Again, here, the stability requirement is embedded here. At the moment, we don't have theoretical guarantees on the convergence. So this is the algorithm. And here again, for this example, a three-player example, we don't have a Nash equilibrium here. So that's why we seek for guaranteed cost equilibria. But here, instead of taking all players' cost to be the same, cost profiles to be same. So here we assume that player 1 and player 3's costs are same, but player 2's cost is different. So then we get actually in a plane. Yeah. So these are all the values of delta 1 and delta 2. All this entire shaded region corresponds to that is values of delta 1 and delta 2, where we have guaranteed cost equilibrium. But for this game, we don't have a Nash equilibrium. But for these values of deltas, this entire region corresponds to the existence of guaranteed cost equilibrium. And the second picture compares the price of stability of these guaranteed cost equilibria with their upper bound. Yeah. And a zoomed version of this is given here. So the minimum guaranteed cost equilibria, that is minimum POS that we obtain is around 1.003. That is very close to the cooperative, that is cost in cooperation. And this is the best upper bound with respect to the guaranteed cost equilibrium. That is 1.017. These are some of the simulation results. And we again, for output consensus problem also, we do the same study here, and we obtain the POS with the guaranteed cost equilibrium with the disturbance to be 1.25. So here we just fix some cost profile. So we did not do for entire this. If we have to do an exhaustive study, it will be in a 5-dimensional space. So we just chose some values and we obtain the guaranteed cost. Again, for this example, we don't have Nash equilibrium. So basically, the conclusions are we studied the concept of guaranteed cost equilibrium, and we provided sufficient conditions for the existence of guaranteed cost equilibrium. And we kind of came up with the discussed LMI-based algorithms for the synthesis of these controllers. In the sense, these controllers can be synthesized using LMI solvers. Basically, that means the synthesis problem is written as solving convex optimization problems. And the stability, one advantage with this approach is that the stability conditions are embedded, but at the moment we don't have theoretical guarantees on the convergence. And this is, I mean, for future work, we are looking at hardboard constraints in uncertain games. So far we only looked at soft constraint criterion, but there are also other criterion like hardbound constraints and so on. Thank you very much for your attention.